The garage is empty today, and luckily all my cars are running for a change, which is a miracle. But today's video is going to be focused on welding. So we're going to demonstrate a new MIG welder from ArcCaptain and see if it can outdo my trusty old blue miller. This has been my staple for almost 20 years. I've had this thing for a really long time. In addition to this, I have a TIG welder. But today's video is going to be primarily focused on MIG for auto body sheet metal repair. So even though my cars are finished and painted and driving and so forth, I still do a lot of videos on welding. And that's because if you own a classic car, like 80%, if not 90% of that car is made of steel. And so you need to be able to repair all kinds of things, whether it's the outer body, the inner body. If you're doing custom stuff, it's a bracket. It's always making a tool or fixing something that's broken. And I think it's one of the most important skills to have if you're a DIY auto hobbyist. This miller is, like I said, about 15 to 20 years old. It's the Miller 135, and that's 135 amps, operates on 110 volts, and it's a transformer machine. This one is 205 amps, and it operates either on 110 or 220 volts. This one's clearly made in China. The miller is made in USA, Appleton, Wisconsin. I'm not sure how many internal parts are made in the USA, but it is an American company for sure. Looks like the old box in a box, maybe. Right away, I noticed this connector is the typical welder connector. That's going to plug in just fine to my 220. And then, like I mentioned, there's this adapter that turns it into 110. You kind of get an idea of the size difference, but this guy is quite a bit smaller. Here's the MIG torch, some wire feed rollers, gas line, solid wire, and the gas regulator. There's pockets on both sides. It's kind of cool. That's where I keep my sleeves and my gloves and whatever I need for that. Plus I have my tools in the back. This just makes it just as well. You can have it right there. I like this one. I'm a dad and a welder. Nothing scares me. Certified badass welder. And I should mention this is a multi-process welder. It will do TIG welding as well, lift arc TIG. We're not going to demonstrate that today. This is strictly going to be a MIG welding exercise. It doesn't actually come with the TIG torch, but I'm sure it's available for not that much money. This line will switch it between positive and negative, so you can alternate these two for different types of welding. So this is the MIG gun, and it has ports for the gas flow as well as electric flow. So we'll go ahead and connect it right here. This is designed as a flexible joint here, which is kind of cool. In comparison to the miller, they're basically the same angles, pretty much the same geometry. This is just a little bit more bulky. So if you're wearing a glove on this hand, it's going to feel a little thicker versus this one's a little thinner. But the trigger position, everything is essentially the same. The nozzle diameters are roughly the same. This one screws off. This one just pushes on and off. So that's it for the setup on the front of the machine for MIG welding. It does have an extra port here, which can be useful if you want to do aluminum welding with a spool gun. What happens with aluminum is the wire is so soft, it's very difficult to feed through this big cable. So you just put the spool right on the end of the torch, and that allows a more efficient feed of the aluminum wire. It also requires a different shielding gas, but it has the ability to add that here. And there's also the ability to add a foot pedal, even a variable foot pedal, which is really helpful if you're doing TIG welding on thin sheet metal. So this wire is too big, in my opinion, for thin sheet metal. It's 035. I've had much better results using this machine with 030 or 023. 023 is probably the most forgiving. Now, I don't have any 023, so today we'll be using 030. So I'll just pull the spool from this machine and load it into this one. For solid MIG wire like is provided, without flux core, it's recommended to use a drive roller with a V groove. There are other grooves, such as a knurled groove and a U-shaped groove. So in this case, it's 0.8 V. Same idea, this roller is interchangeable for different wire thicknesses and wire types. There are more metal components in the Miller machine. This is ER70S6 wire 2. I'm holding on to this to make sure it doesn't just unwind. So let's get this fed through first. We'll clamp it in position and then we'll sort out the hub in a second. So there is some tension on the wheel. That's to prevent this from just unwinding on its own. So there's a little bit of friction there. That seems about right. Doesn't seem like it's as adjustable as the Miller, but that'll keep it from unwinding on its own. I'm going to be using the same shielding gas bottle for both welders. So I'm going to use the new regulator that came with the ArcCaptain. This one shows the tank pressure, and then this will show the flow rate. So we'll go ahead and attach this and we'll try it out. Now I like to feed the wire through with no tip at all. That way there's no danger of it getting stuck on the fitting. It is beveled, but let's feed the wire through. So at some point, that wire should come out the end of the nozzle here. Yep, there it is. It's a good idea to make sure all this brass stuff is tight because this is where the electricity actually flows through. So it comes with this wrench. Doesn't seem to fit very well, but what I like to do is, it's about equal to the nozzle thickness, or the nozzle diameter is about how much I do stick out. It seems like it's gripping the wire really well. Just curls it up. So if you're seeing it slip there, that's where you would want to increase the tension. I don't see any slippage on it at all. So that's perfect. So see that ball jump up? 15 or 20. So that's about what I want to be. I've had a little bit of time to run some beads and just get acquainted with the machine, and it's actually really quite good. I've stuck together a few pieces of metal and just played with some settings and actually learned a few things about the machine too. So I'm going to show you what I learned, and I'm going to tell you how I go about setting up the machine to make sure I get consistent welds for thin gauge sheet metal. So it defaults to amps and volts, but if you're used to using the Miller machine like I am, it uses volts and wire speed. You can push these buttons and it'll toggle between different settings. So I was just on amps. This will display inches per minute, and then I can click it again. This will display, I think this is metal thickness. The last one is job number, and I think you're able to save settings as a particular job number. This is volts from 1 to 10. It's just an arbitrary scale. And then this is wire speed from 10 to 100, which is also arbitrary. But it kind of makes sense for me to toggle this to inches per minute. And as I change the wire speed, it's in the synergic mode, or synergy or sync. So it's automatically going to reduce the voltage to correspond with the inches per minute or the wire feed rate that I want. Now, if you turn the synergic off, or synergy or synchronize, whatever you want to call it, this will give me full independent control. And now when I change the wire speed, it does not change the voltage. So I can, for whatever reason, if I want to go outside the manufacturer's recommendations, I can do that. So I've been keeping it in the synergic mode, and I just kind of like being able to select my inches per minute or amps or thickness, whatever you want to do. Same with this button. You're able to click it and it'll change a couple other settings. The first button is the burn back. So on the torch, when you're done welding, the stick out length can sometimes change. So I just grabbed the gun, and the amount that the wire sticks out is important when you start and stop your weld. So you can adjust that parameter here by hitting one button, and I can increase the time the welder is going to burn, or I can decrease it. And that's going to affect how much stick out is left after I'm done welding. That's really helpful. And then hit it again, there's something here called inductance. And I haven't played with this too much. I'll try to show you guys if I can even notice any difference. But you can go from -10 to +10, and we'll try that. That's a setting you probably aren't going to want to mess with, but we'll try it anyways. And then this is the voltage setting. It's just a fine scale tweak to whatever the machine thinks it needs. So it thinks it needs 13.4, but if I want to just give it a little bit more, I can adjust it up or down by 3 volts. And that's a pretty significant range. So I like the synergic setting. Even for an experienced welder, I think it gets you right in the ballpark. But for setup purposes, I'm going to take that off and show you how I go through some of these settings for the type of metal that I'm using. So if we look at some of these practice beads, you'll see this one here is really narrow. And then this one here is really wide. So these are some of the settings that affect it. This bead right here is a pulsed bead. It kind of has a stack of dimes appearance. This one here is also a pulsed bead. Look how narrow this one is. This one is super wide. You know, this one here burned through. This bead right here is really flat. This one's kind of tall with a big lump on the end. So I'm going to show you what to look for as you're setting this up, and also go through some actual welding exercises, like here's a butt weld. And by all means, you know, start with the settings here on the chart. So 19 gauge, the bigger the number, the thinner it is. It's a little easier to follow in millimeters, but I'm actually doing 20 gauge, which is even thinner than 1 millimeter. So I'm dialing the machine back just a little bit. But I'm going to start with the smallest, lowest setting and look for how stable the arc is and explain why you might not want to run the lowest possible setting. So I put the machine down as low as it'll go. It's 11 volts and 60 inches per minute, and the synergic setting is off. So if you're nervous about burning through, which most people are, on thin gauge metal, you'd probably think like, oh, this is going to be the best setting. I just don't want to burn through. So this is the result, and the bead is very proud. So this is like an 1/8 inch stick or barbecue skewer, and it's probably as proud as it is wide. So it's real narrow, it's real tall, and the arc stability was not good. Basically, you can see little droplets kind of burning off the electrode and just laying on top of the metal. You look at the back and you can see there's a mark on the back, but there's no real penetration coming through. So let's go up to something like 70. The arc was more stable that time, but we're still getting a very narrow bead, and it's still very tall. So let's look at the back side. Still no penetration really to speak of, but the arc stability was better. The weld was a little bit more consistent. So let's go up another 10 on the wire speed and see if that improves things. This is 80 inches per minute, 11 volts. So this time, there's not much change between the 70 and 80 inches per minute. So this is probably the sweet spot for this particular setup. But I'm gonna go up to 100 inches a minute, probably over speed, and see what that starts doing. On this one, this was 100 inches per minute, and the arc started becoming erratic again, and the weld is even worse. It's even taller. There's really to little no penetration on the backside. This one was the best weld. It had some penetration on the backside. This one is marginal on the back. So in this case, in order to get this to be flatter, I'm going to increase the voltage quite a bit. So the minimum settings do weld, but it's not considered a great weld. This would require tons of grinding, and I just don't like the appearance of it. So I've moved the machine up to 20 volts and 140 inches a minute. The higher the energy, the higher the amount of wire feed is necessary. So this is an arbitrary guess. I just want to show you guys what happens when you guess. So that was a dramatic change. Let's go back to like something 15 and a half, and I'm going to keep the wire feed the same, 140. That was a better setting, but it's still too hot. I'm burning through the metal. So let's back it down just a little bit more. Let's do 13.5, and I'm going to reduce this to 130. Okay, that was much better. I think I might have traveled a little too slow in the beginning, but now we're getting a much wider and flatter bead. So we're getting close to an ideal setting. This is penetrating through the back as well. So I'm going to turn the wire speed down a little bit and see if we can get a nice wide flat bead. That was a little bit more consistent. The arc was a little bit more stable, but we're still getting a pretty proud bead. So I think what I might need to do is kind of go back to something like this, but just travel faster. So that reduces the total amount of heat put into the panel. All right, this one is probably the best one out of the bunch. And this one is at 15 volts, 120 inches per minute. And I increased my travel speed just a little bit. And that gives me a much flatter, more consistent weld bead. Backside is nowhere near burning through. It's just pretty good there. So I'm going to move the machine now to synergic mode and see how it compares to what I selected. So I'm now in synergic mode, and I am toggling here for metal thickness. So this looks like it's not thousandths of an inch. This looks like it's a sheet metal gauge, because the lower I go, the higher the number. So 21 gauge is, I have 20 gauge, but it jumps between 19 and 21. So I'm going to set it here for 16 volts, and the adjustment here is zeroed out on the trim. So it's got me at 16 and a half, 89 amps, which would be for 21 gauge metal. And interestingly enough, the inches per minute on this is way up, 199. I'm going to run these on this side. It did burn through, but let me do a little quicker travel speed and see if we can avoid that. Nope. This weld bead here is actually pretty nice, but you got to travel pretty fast. The penetration, these obviously are way too much, and then this penetration is still pretty significant. Probably a little too much. So I think what I'd like to do is adjust it down just a little bit. I'm going to go down, maybe 2 volts, and then try that one more time. So still in synergetic mode, I'm just going to go minus 2.0 and see what happens. Okay, this one here is probably almost identical in appearance to this one. This was the manual setting of 120/15. This is the synergetic setting, and it only took me like 4 tries here, whereas this one took 1, 2, 3, 4, 5, 6, 7, 8, 9 different tries. So I kind of like this synergetic setting. Started slow, I sped up a little bit right here, see how it's narrow? And then right here at the end is pretty much the perfect profile for this thin metal 20 gauge. And there's the back, still a lot of penetration, which, you know, for 20 gauge, that's kind of hard to avoid. I kind of like where it's set right there. Let's do another bead and try to keep the travel speed a little bit more consistent. This one might have been better. This one's pretty good. Okay, same settings, a butt weld, and I'm gonna try to do it in one continuous weld. So I think I sped the travel speed up just a little bit because I know how difficult this is to join a seam like that. So we did get a burn through, pretty minor, but that did happen. Penetration on the back is pretty good. So the trick to avoid that little burn through is tough, I'm not gonna lie. You'd think you just need to travel faster, but I find that it's really difficult to control your travel speed with the MIG torch. It's just something that you can't control. I'm actually moving pretty fast, and that's a little bit over an inch at a time. It's hard to travel that fast and control the arc length and control the travel speed. It's basically just too much too fast. So the trick is to use what we call pulse weld or on-off. So I'm gonna weld like a spot weld or a tack weld. I'm gonna wait for that to cool, and then I'm gonna advance forward and do it again. And I'm just gonna keep welding on top of the previous weld until it cools. So I didn't change the weld settings at all, I just changed the approach. So I was able to slow down and control what I was doing here, and I got a much more consistent sort of bead. So the width is pretty good, much wider than here because I wasn't traveling as fast with the MIG torch. And that's a good weld. You would have to grind it down, of course. Backside is completely penetrated through. So that is the setting that I would use for welding 20 gauge. I'm gonna show you again on a new piece what it looks like through the welding helmet. I have a lens for my camera. I'll try to give you guys the actual arc shot of what it looks like and what I'm doing. I know it's going to be hard to see behind the welding helmet. The camera is difficult to set up on those, but hopefully that had some benefit to you guys. This is the weld bead that I just did, and this is 2.5 inches long. I would never weld this much on a car in one swoop. So you can see how much the panel is heated up. This width right here is about 1 inch, and we like to keep that as tight as possible when welding on like a fender or something, because the distortion becomes a real problem. And sure enough, this thing has quite a bit of distortion to it. The weld is good. It's mostly just welding practice. But if this was in a car, I would skip around. I would start here, I would go here, I'd let it cool down, I would skip back and forth, especially if it's on a big panel. You know, you'd work on the front of the wheel arch, the back of the wheel arch, the middle of the wheel arch. You got to skip around, otherwise you're going to have a bunch of distortion to deal with. But I'm really happy with the machine. The settings are great. The one thing about this pulse technique is that the wire stick out or the burn back has to be the same every time. So what I'm trying to do as a welder is keep the arc length the same. That stick out length has to be the same. So once the machine's set up, the machine does most of the work. My job is to make sure that I have enough control of the torch that I'm keeping the torch consistent. So what I like to do is I'll use my left hand with this heavy glove and sleeve on it, I'm wearing a long sleeve too, is I brace the nozzle with this hand. I'm not using this like a baseball bat and trying to, just free willy out here. I am using this hand for support. That's why this glove is all beat up. I do it all the time. So the angle is also important. You want to be, vertical and then maybe like 15 degrees back at the most. So I'm using my elbow way up high to keep the torch consistent. Now all I'm doing is I'm just advancing along. I'm pulsing, waiting, pulsing, waiting, pulsing, waiting. So I can't let this come up, because if I do that, the machine settings are totally different now. It's not getting good shielding. It's just not going to give you consistent results. So the burn back is important, because every time I stop, I want this electrode to be exactly where I started, which is about 1/2 inch, 3/8 of an inch. So if I can keep this stable, stop, start, and I'm not lifting or shortening this too much, I can get a consistent weld bead. If I turn it too far this way, I can see better, but now the shielding and the penetration is completely different. So you want it to be vertical, like a robot. If I was a robot, I'd probably have this 5 degrees max. But I gotta bend my head over to see what I'm doing, and I gotta use my left hand to keep it consistent. I'm using my right hand only to pull the trigger, and the left hand is giving me all the consistency, and I can just guide along. Just rotating my wrist, I can guide that along. That's what I think is the trick to getting a good weld. Obviously, your results may vary. And then I do wear these reading glasses underneath my helmet. It just helps me see. And every person has to adjust their sight distance. The helmet to workpiece distance can be different for every person. So I like to get pretty close, but that's because I have the readers on and I can see better. There's the back side of that last one. Really consistent penetration on that one. That's the top side. The arc stability is great. The on-off stability is awesome. The burn back the default was set perfect. I don't have any complaints at all with the welder. It's performing really well. I'm just curious about that inductance setting. I've read that higher inductance can work better on thin sheet metal, because it doesn't hit that first arc. It doesn't hit it as hard. So the risk of burning through is a little bit less. So I'm gonna go all the way up on the inductance and see if I can actually tell a difference. So that inductance setting is available even in the synergetic mode. You gotta hit this twice, and I'm gonna turn it all the way to 10. It's plus minus 10. So let's try plus 10, minus 10, and see if we notice any difference at all. This is an advanced setting. I think it's gonna be a subtle difference. The current ramps in just a little bit slower. It's not hitting it as hard. It's welding just fine. So now before I finish, I'm gonna go to the negative inductance setting and see if I can really tell the difference. This one was with the maximum inductance, and it's just a little bit of a softer profile. This one has more definition, and it is, I mean, it welds about the same. I didn't start it very well. I was off to the side, but I got back to the center. They're both fine. I kind of prefer this one over this one, only because this one just seemed like a more gentle start. And so I kind of like that. Maybe just do like a +5. The backs of the welds are pretty much the same. So these panels weren't fitted up very well together, so there's an offset here. I didn't even correct it, but penetration's about the same for me. But if I had to pick between these two, I would probably pick this one. This one has a couple craters in it, and that's usually from rapid cooling. So if the current ramps off too quick, it can cause the puddle to just collapse, and you get that little crater in there. I don't know if that was from the inductance or not, but I didn't get it on this one. So maybe it's just because I stepped forward a little bit more on these and the puddles, the crater is visible. So another setting that this machine has, if you hit, I think it's this button, this will do what's called spot welding. Spot welding, it's spot welding, but not in like the resistance welder where those two, metal tongs come together and pinch the metal. I don't think it's that kind of spot welding. It doesn't come with those tongs. But I think what it means is that you're able to do what's called rosette welding or plug welding and let the machine kind of do the work for you. So it's going to give you some timer settings. And so I want to try that because that's one of the real benefits of MIG welding is doing a lot of overlapped metal. When you want to join two pieces of metal together, like say a floor of a car or something, you're gonna pinch them together with either screws or clamps or whatever, and then you're going to drill a hole in the upper panel and then weld that hole closed and penetrate into the lower panel, so you've effectively spot welded it. And you can do that like in a floor, you do that like 100 times. So if the machine has an ability to help you with that, that would be amazing. Now I'm on spot mode, and if I hit this button, it gives me an option of adjusting this guy. So I can do spot welds from 0.5 seconds all the way up to, looks like 5 seconds. So you can use this as a pulse technique too. I'm gonna do like 1.5 hippos. I think that should be good. Before I drill some holes, I'm just gonna continue on this bead and see what it does. So 1.5 seconds is too long. It does burn through. So say for instance, I want to continue on that, that pulse method. Let me try 1/2 second. So what happens is I'm holding the trigger down and the machine just stops. I'm still holding the trigger down. If I let off and I pull it again, it'll turn back on. So this keeps me from putting too much heat in the part. It's automatically turning off. So this is at 1/2 second, and I got a real wide bead because I'm not advancing very fast. I kind of prefer to do it manually, but the machine will do that for you. So this hole punch makes nice clean holes, so let's make a bunch of them. Okay, so the way a factory builds a car is typically with big pinch welders, and they just resistance weld over and over again until the car creates that lap joint. In our case, as a repair person, the car is typically already built, so you're not able to take it all apart and re-weld it in the same order they did. So we don't have access with the tongs or the equipment that they had when they built the car originally. So that's why this method is kind of the industry standard on joining metal together, where you don't have a big pinch welder or you don't have access like they did when they first built the car. So you want the panels to fit pretty tight. You can hit it with a hammer, try to tune it up a little bit, make it as tight as you can. But that looks pretty tight, at least on this side. I start in the center and then just move around. So in that case, I didn't fill the hole because the machine turned off too soon. So let's bump that up to 1.5. Maybe that's a little too long. Let's see. This is 1.3 seconds. Let's see how we do. So these are, still standing pretty proud. I might want to increase the heat a little bit so that these are going a little bit deeper. And also, you can see like this penetration here was good. This one here was maybe not so good. So depending on the total time and the heat settings, you can dial these in perfect. So I'm gonna go up in heat and see if I can get one that requires almost no grinding. I'm gonna zero this side back out. That was the trim. And then I'm going to, so I'm at 16.5. I'm gonna increase the amperage to about 95. That increases at 0.5 volt. Let's just go to 100 amps even and see what happens. That one was pretty good. So this weld right here is pretty flat. So if I put my stick over it, you really can't tell anything about that. It did have a crater, and that's probably because it's a pretty high current, and it just, that's the thing with MIG welding, is the current just stops pretty quick. So other than that crater in the middle, it's really not bad. I did this one and this one with the higher current settings, and the penetration is better and the weld is flatter. So this would require very little grinding. That's not bad at all. So I've done so many rosette welds over the years that I still probably prefer the manual method, just because it's sort of baked in as muscle memory maybe. But the settings are really nice that the machine can do that. It does give you more consistency, and it's kind of prevents you from holding the trigger too long. If you're a beginner and you're welding along and you feel like you're doing a really, really good job, the machine can prevent you from holding it too long and creating too much heat in a panel. I've done other welding videos too, particularly on simulated spot welds was kind of a popular one. I think a lot of you guys like that. It's a little bit over the top, but I'll put a link to that video right here. We covered the setup with too cold, too hot, wire speed too low, wire speed too high. We talked about the profile bead and what it means to get good penetration. The machine is capable of definitely restoring an entire car. It's very, very capable. So I guess what's left is to actually demonstrate what it's like to weld on something that's not perfect. So one of the advantages of MIG is it's pretty tolerant to like dirty metal. Of course you should clean it, but as opposed to TIG welding, the MIG can really combat like dirty metal. A little bit pitted. A lot of cars, you're repairing rust, and so things aren't perfect. I was demonstrating panels that fit together pretty easily, pretty nice panels that have very little gap. The MIG is really good at filling up big gaps. So if your panel fit is not that great, MIG welder is a good choice because it's got so much filler, it can fill up gaps. And so I'll try to demonstrate that. This is an actual Porsche part. It's the bottom of a door for a 64. These are available new, so I elected to just replace the entire thing. But this one does have some rust holes in it. There's a rust hole right there. The whole edge where the door seam gets crimped on is rusty. and there's, you know, real thin spots in it. This whole section here is very thin and pitted and rusted. So let's just do something like, I don't know, let's just fix this rust hole here. So I'm gonna start with my wire wheel and just clean up this metal so we can see what damage is there. Hopefully you can see there's some pitting around the hole. And I originally thought this was a rust hole, but I think this might have been a spot weld that was ground out, because now I can see some grinding marks on it. But either way, let's just say that this is something that needs to be filled. I think this was also ground out. So the question is, you know, can you just fill this with MIG weld, or should we create a patch panel? And so I think I'll try a little bit of both. This one's a little bit larger, so let's do a patch panel. In this one, we'll just turn this into kind of a round hole. And then on this one, we'll just try to fill it up with MIG weld. I'm gonna enlarge the hole on purpose. Okay, so now, you know, we're left with that hole, which is not perfectly round, and that's okay too. But that's about 3/4 of an inch. So I'm gonna trace that onto some paper and then transfer it to one of these sheets of metal, and then we'll weld it in. So my grubby fingers just transferred that hole perfectly to the piece of paper. These curved scissors kind of help for these nice round shapes, but it's not necessary. It's like a coloring book, but not coloring in the lines. So we just do that, and then what's left is this blob in the middle. We want to remove all the ink. That side's just a little bit loose, but it's okay. The welder will do fine. We'll try to just give it, it's holding itself reasonably well, but I thought it would be helpful to have at least one clamp on there. All right, so the initial welds are done. So now I'm gonna do just one quadrant at a time. That's about, I would say, 1/2 inch at a time. Go from tack to tack and just use that pulse method until it's solid. Okay, I think I forgot to turn the camera on that one, but this branch here is now bridged together. So I'm gonna let that cool. I'm gonna skip to the opposite side, let that cool, and then we'll do top and bottom. Let that cool. So the interesting thing to note on this one is you get this kind of like orangey, rusty color, and that is because this is old metal as opposed to this, which is, you know, brand new metal. You get a little bit of oxidization when you're welding something that's not perfectly clean. The backside is got a lot of penetration. This metal is super thin. You know, this is a sports car. This thing is very light. And let's just wire brush it and see how the weld itself looks. So I can see that the weld is a little bit tall right there. It's just going to require grinding, and you know that's the disadvantage of MIG, in my opinion, is it's messy and it requires a lot of grinding. This is probably due to contamination in the metal, and it starts to kind of erupt into a little stalactite or stalagmite. These are typically hollow because it's just full of gas inside. It's not ideal, but when you're dealing with something this old and dirty, this is typically what you get. Now I'm using a cutoff wheel. It's actually my preferred tool. I'll do a two-step process. One is the grinding wheel to get the bulk of the material off, and then this is a sanding disc, 2-inch sanding disc that'll do the rest. So with the cutoff wheel, I only try to target the weld, nothing surrounding the weld. So I'm just trying to knock down the really high profile. Now I'll try to blend it with this roll-lock disc. There's still some evidence of the weld, but at this point it's got a little bit of a depression to it. It was actually sunken in before I welded it, but at this point it's time to hit it with a hammer, try to kind of flatten it out, smooth it out a little bit, and then we'll come back with a grinder again and try to make this weld disappear. Backside, is the backside. It doesn't need to be perfectly smooth, but I want it to be smooth enough, like for instance that big stalactite. I wanted to get that off of there because there's no point hammering on dolly unless it's smooth to some degree. I'm just going to use this ball peen because the welds are hard enough to actually dent the hammer sometimes. All right, so the hole is gone and the finish is pretty smooth. It's got not much work done to the backside, but you can kind of leave that alone. There's one little pinhole right about there. That is part of the weld bead, and that's that stalactite on the back. So that was due to contamination. It's just the way it is. Let's try this one without using a patch. Let's just try to weld it up. I think I forgot to hit record on that one. I did fill that hole. Let me do it again on this hole down here. I was not wearing a welding glove. I was just wearing a kind of a latex thing. It still didn't get hot. Use this hand to stabilize the torch is kind of what I mean. But this is dirty because it was a dirty metal to begin with, but it is filled up. So let's just wire brush it and see there are some stalagmites on the bottom. So this would need to be ground on both sides, but the hole is gone. I think that looks like a hole there, but that does not go through. You might want to just hit that one more time, one little burst, but I prefer to do this. I think this gives you an overall cleaner repair. than this. This is going to require a lot of grinding. It's going to be really hard to hammer it because it's all filler metal, which is effectively like cast iron. You can't really move it that much. So if I had to do this on a car that I really cared about, I would make the hole larger and put the patch panel in. Here's the other one that I filled up. This hole was a little bit bigger. So most of the bead is pretty level, but it's just ugly and messy. It's just a lot of start and stops. It's got some porosity in it. It's not ideal. One thing you may have noticed when I was welding these holes closed is that I went a different direction with the MIG torch. So normally I go right to left and I push the weld along. But in this case, I went left to right and I pulled the weld through. The reason being is that you need mass in order to have something to weld to. So for example, if I was to weld this seam right here, it has a very large gap. From this way, like right to left, I'm basically welding in mid-air. So that tack weld is now something that I can start the process on. So I'm gonna start right on top of that bead and I'm gonna drag it over the open air. So each time I hit the trigger, instead of aiming it at air, I'm aiming it at the previous weld. Now I have to weld slower because, like I said, I'm basically welding air. So if I hold the trigger too long, it's gonna erode each of the base metals and it's gonna create like a hole. But if I go slow, I can just pull a new tack right over the empty, basically air. Ignore this part right here. That's where the gas was not on and I had a big burst of basically just contaminated metal. But these little bursts here are just filling up this big gap. And I'm gonna go all the way to the end and I'll take that clamp off. It's possible to weld something that's probably 2 or 3 times wider than the actual thickness of the metal itself. It was, you know, pretty wide, and I was able to fill it up with the pull method. You should make your panels fit as best as possible because I had to spend a lot more time with the welder. I'm going on and off, on and off. It uses more gas, and this is going to be harder to metal finish. You know, the back is all messy. Some wire is poking through right there. It's called a little whisker. So it's possible, but it's not recommended. The other thing to consider when you're working on a car is some thicker stuff. Now I work on like sports cars that are unibody construction, so not a lot of real thick metal in them. I think that's probably pretty good. I'm gonna go a little less on wire feed. The wire speed was a little too high. Same with that one, it was a little too high. So when I lowered the wire speed, I got a little bit flatter, profile. So these are not butt welds, these are fillet welds, but they're pretty good. So this is what the settings were for the miller. That one gets TIG welded because I don't want to grind anything, and it's just faster for me to just do a TIG weld on that one. But that's, real similar results. Miller here versus the ArcCaptain here. I thought the ArcCaptain did really well. I do notice it sounds a little different when doing the thicker metal. So the inverter, I don't know why, but it just sounds a little different than the old Miller machine. It welds just fine. It just sounds like it is not getting enough gas flow. But when you look at the weld, it's got plenty of shielding. So it's just, I think, a difference in the technology of the machine. But the weld quality is great. So personally, I think my plans for this machine are to put it through production paces. Like, I'm gonna use it for those engine stand adapters. There's times where I'm welding for like 4 hours straight, and the Miller, when it's set to 10, will eventually duty cycle out, where it needs to kind of cool down. This will allow me to not have to do that because it operates on 240. And I don't think it's gonna duty cycle out at the sort of settings I have it on. So that'll be a big test for it. So, you can always reach out to me in the comments below, or my email is in the About page. If you need to email me, if you have particular questions about either welder, I'd be happy to work with you guys offline. This is an affiliate product, so I do earn a commission if you buy this using my link in the description below. I think you also can get a discount on the machine. And I'm saying that in complete transparency. I wouldn't give you this as an option if I didn't think it was good. I'm personally considering, selling my Miller and going with this full time because it can outperform the Miller and has a lot more settings. It's got a lot of things that the Miller just can't do. And if you've watched some of my other videos, you know that I'm a big fan of TIG welding. This machine does do TIG welding, DC only. So you cannot do aluminum or any other non-ferrous metal. You need an AC machine for that. I have an AC machine. I occasionally do aluminum. This one would work for steel or stainless, or if you do want to do aluminum, you would need to get the spool gun and run it in DC mode, just like a MIG mode. My personal preference is still with TIG welding on thin automotive sheet metal, especially outer body stuff that you really want to metal finish nicely. I have another video on the difference between MIG and TIG, and I'll put a link to that one right here. It has a softer weld bead. It's easier to metal finish. I think at the end, you get better results. The result I got on that door bottom was perfectly good. You can use either machine and get perfectly good results. You can restore an entire car with just a MIG welder. I'm not saying MIG welders aren't good. I just think personally, if you're really after the 10/10ths of metal finishing, you're gonna have better results with TIG welding. I personally think that the amount of time with TIG welding is about the same. You spend less time on grinding and metal finishing and filling with Bondo. So to me, it's a wash. The requirements on TIG welding are a little higher in terms of skill level. I do offer occasionally in-person welding classes. It's here in this shop. It's limited to 4 people. It's a group day. We just cycle through. If you want to use MIG, we can. I prefer to teach with TIG welding. I prefer to start with TIG welding. And then as the class goes on, if someone wants to use MIG, we'll definitely use it. You can try this machine or the Miller machine. I would probably set you up on this one first because it works really well. So I would recommend get the welder, get the shielding gas, get the O23, get a helmet that has good viewable area. That's a auto darkening helmet. And you're off to the races. After that, it's just practice. I can definitely tell you this machine here is not the limiting factor. It's basically just practice and perfecting your technique and getting more control of the MIG gun. The only thing I can see negative about this machine that I actually like the Miller better is I like the regulator system and the argon CO2 flow rate meter a little bit better on the Miller. I just like those dual gauges instead of the ball that bounces up and down. They're both equally valid. I've just been doing this so long with the Miller and I've just got accustomed to looking at that gauge. We talked about some of the plastic components inside. You know, the advantage is it's lightweight. The disadvantage is maybe it's not as robust, but I can tell you for sure that the wire speed control and the stability of the wire control is great. I had no issues with setup or adjustments. You got a lot more detail with the digital display than you do with the Miller. The Miller is an analog potentiometer kind of thing, and you don't have the same finite adjustment as you do with this one. This one you can adjust 1/10 of a volt, something like that. That's not even gonna make a difference in your weld, but the machine can actually do real precise adjustments, and it's easier to program it, come back to it. Your settings are right there. It's easy to get the same results every single time. So the only thing that time will tell is how good is the reliability on it, how good is the stability after a couple hours when it starts to heat up. I can tell with the Miller welder when it starts to get warm, some of the settings change a little bit. It'll be interesting to see with this machine if the stability, once it's been running for a few hours, is the same as when you first turn it on. Thanks again, guys, for watching this video. We'll be back on an actual car project next week, so we'll see you then. Cheers.